I am Dr.L.Madhuchelvi, Associate Professor of Mathematics, Sri Sharada College for Women, Salem. In this session, we will talk about Simplex Method. First, let us say what is called a linear programming problem. The linear programming problem deals with the optimization of a function of decision variables known as objective function, subject to a set of simultaneous linear equations known as constraints. The term linear means that all the variables occurring in the objective function and the constraints are of the first degree in the problems under consideration, and the term programming means the process of determining a particular course of action. First, let us say, what is the general linear programming problem? The structure of a general linear programming problem. The linear programming involves more than two variables may be expressed as follows. Maximize or minimize z equal to c1x1 plus c2x2 plus c3x3 plus and etc. plus cnxn. Subject to the constraints a11x1 plus a12x2 plus and etc. plus a1nxn less than or equal to or greater than or equal to b1. a21x1 plus a22x2 plus and etc. plus a2nxn less than or equal to or greater than or equal to b2. a31x1 plus a32x2 plus and etc. plus a3nxn less than or equal to or greater than or equal to b3. And so on. am1x1 plus am2x2 plus and etc. plus amnxn less than or equal to or greater than or equal to bm, and the non-negativity restrictions x1, x2, x3, etc. xn greater than or equal to 0. Let us see the definition of a solution of LPP. A set of values x1, x2, etc. xn which satisfies the constraints of the LPP is called its solution. Then what is called a feasible solution? Any solution to a LPP which satisfies the non-negativity restrictions of the LPP is called its feasible solution. Then let us see what is known as optimum solution. Any feasible solution which optimizes, that is maximizes or minimizes the objective function of the LPP is called its optimum solution or optimal solution. Now, let us see the definition of slack variables and surplus variables. If the constraints of a general LPP be summation j equal to 1 to n aij xj less than or equal to bi, I equal to 1, 2, 3, etc. k, then the non-negative variables si, which are introduced to convert the inequalities to the equalities, that is summation j equal to 1 to n aij xj plus si equal to bi, I equal to 1, 2, 3, etc. k are called slack variables. The value of these variables can be interpreted as the amount of unused resource. Next definition is surplus variable. If the constraints of a general LPP be summation j equal to 1 to n aij xi greater than or equal to bi, then I equal to k plus 1, etc. Then the non-negative variables si, which are introduced to convert the inequalities to the equalities, that is summation j equal to 1 to n aij xj minus si equal to bi are called surplus variables. The value of these variables can be interpreted as the amount over and above the required level. Next, let us go to the simplex algorithm, that is used to solve a linear programming problem. So, assuming the existence of an initial basic feasible solution, an optimal solution to any LPP by simplex method is found as follows. Step 1, check whether the objective function is to be maximized or minimized. If it is to be minimized, then convert it into a problem of maximization by minimize z equal to minus of maximize of minus z. Step 2, check whether all BIs are positive. That is, all the BIs. The BIs are here. Then the general programming BIs are this RHS variables B1, B2, B3, etc. So that BIs, all BIs are positive. If any one of the BI is negative, multiply both sides of that constraint by -1 so as to make its right-hand side positive. By introducing, step 3, by introducing slack or surplus variables, convert the inequality constraints into equations and express the given LPP into its standard form. Step 4, we have to find an initial basic feasible solution and express the above information conveniently in the following simplex table. That is initial simplex table. Here, that Cj, see the table, Cj, the row denotes the coefficients of the variables in the objective function. That is, in the objective function, we have z equal to, maximize z equal to c1x1 plus c2x2 plus c3x3 plus an etc. That c1, c2, c3 should be entered here. Next, CB. CB in the first column, CB denotes the coefficients of the basic variables in the objective function. Then YB. YB is column denotes the basic variables. What are the basic variables? XB column denotes the values of that basic variables. Then X1, X2, X3, etc. are the coefficients of the non-basic variables in the constraint equations that constitute the body matrix, while the coefficients of the basic variables constitute the unit matrix. That is, the slack or surplus variables, slack variables coefficients, S1, S2, S3, that constitute the unit matrix. The row, here in the table, here it is, row is a J minus Cj. That row denotes the net evaluations. Net evaluations. Then next, step 5, compute. How do you compute that net evaluation? Is a J minus Cj. That is by using the relation CBAJ minus Zj. So we have to multiply that CB by AJ, that is A11, A21, A31. That gives you CB1, A11 plus CB2, A21 plus CB3, A31. That gives you Z1 minus C1. C1 is here in the top row. That is the way of computing that Zj minus Cj. After computing all the Zj minus Cj, we have to examine the sign of Zj minus Cj. There are two options. One is if all Zj minus Cj greater than or equal to 0. Second one is at least one Zj minus Cj less than 0. Suppose if all Zj minus Cj greater than or equal to 0, then the current basic feasible solution XB is optimal. If not, that is at least one Zj minus Cj less than 0, then the current basic feasible solution is not optimal. So we have to go to the next step. That is, we have to find in this step, step 6, we have to find the entering variable. How do you find? The entering variable is the non-basic variable corresponding to the most negative value of Zj minus Cj. That is, if any one or more than one of Zj minus Cj less than 0, then we have to choose among that most negative. So that most negative value is the corresponding to that most negative value of Zj minus Cj. The non-basic variable is there. That is the entering variable. Let it be XR for some j equal to R. The entering variable column is known as pivot column, which is shown marked with an arrow at the bottom. If more than one variable has the same most negative Zj minus Cj, then we can choose any one of this variable as the entering variable. Next, step 7. Now we find the entering variable. So we have to find now the leaving variable. So for that we have to compute the ratio theta equal to minimum of xbi by air. Say, see the table in this xbi by air. That is this one. Suppose this is a 2 minus C2 is most negative means. Here we have to find that ratio as theta equal to minimum of that B1 by A11, B2 by A21, B3 by A31 and so on. That is XB by minimum of XBI by AAR. What is the condition is AAR should be greater than 0. Then only we can find the denominator should be greater than 0. If all AAR less than 0, then there is an unbounded solution to the given problem. If at least one AAR is greater than 0, then the leaving variable is the basic variable corresponding to the minimum ratio theta. If theta equal to XBK by AKR, then the basic variable xk leaves the basis. The leaving variable row is called the pivot row. And the element at the intersection of the pivot column and pivot row is called the pivot element. The next step is we have to drop the leaving variable and introduce the entering variable along with its associated value under CB column. Now convert the pivot element into unity by dividing the pivot equation by the pivot element and all other elements in its column to 0 by making use of the formula new pivot equation equal to old pivot equation divided by pivot element. First one. Second one is new equation, all other rows including Zj minus Cj row equal to old equation, already existing equation minus the corresponding column coefficient into new pivot equation. That is, which one we have to make it 0, that column coefficient into new pivot equation. Then using this method, we can find all the rows, the 3 rows, the 3 new rows and new iteration table 1 is constructed. Step 9, go to step 5 and repeat the procedure. That is, for this new table, as it is in step 5, we have to find the Zj minus Cj and we have to check whether all Zj minus Cj greater than 0 or less than 0. If all Zj minus Cj greater than 0, we obtain an optimal solution. Now, let us see an example using simplex method to solve the LPP. The problem is maximize Z equal to 4x1 plus 10x2 subject to 2x1 plus x2 less than or equal to 50, 2x1 plus 5x2 less than or equal to 100, 2x1 plus 3x2 less than or equal to 90 and x1 comma x2 greater than or equal to 0. Then by introducing first, what is the first step? We have to convert the given equations, given LPP into standard form. Standard form, that is, we have to check first all the BIs are greater than 0. If it is so, then we have to add the slack variable with the slack variable to the equation. First S1 to the equation 1, S2 to the equation 2 and S3 to the equation 3. So correspondingly, we have to add in the objective function also with the same slack variables with the 0 coefficient. So 0s1, 4x1 plus 10x2 plus 0s1 plus 0s2 plus 0s3. It is the objective function. Subject to the first constraint becomes we are adding the slack variable s1. So 2x1 plus x2 plus s1. For the other two variables, we have to give 0 as the coefficient. So we are having 0s2 plus 0s3 equal to 50. Like that, similarly, adding S2 in the second equation and S3 in the third equation and getting the corresponding other terms are 0. Then, and finally, we have to write the non-negativity restriction. So x1, x2, s1, s2, s3 all are positive. That is greater than or equal to 0. Now, since there are three equations with the 5 variables, the initial basic feasible solution is obtained by equating 5 minus 3, that is 2 variables equal to 0. The 2 variables equal to 0 are x1 and x2. They are called non-basic variables. So x1 equal to 0, x2 equal to 0. If you substitute these values in the constraints, we are getting the values of s1, s2 and s3. That is s1 equal to 50, s2 equal to 100 and s3 equal to 90. Then now let us form the initial simplex table. So as in the step 4 in the algorithm, here we are going to construct a table. First Cj. Cj denotes the coefficients of the variables in the objective function. So what are the variables in the objective function coefficients? Here 4, 10, 0, 0, 0. So we are entering here 4, 10, 0, 0, 0. Next, we are going to fill up CB. What is CB? CB denotes the coefficients of the basic variables in the objective function. The basic variables are here S1, S2, S3. So the coefficients of S1, S2, S3 in the objective function is 0, 0, 0. So here we are noting the entering 0, 0, 0. Next column is YB. YB is the variable column, basic variables column. So here we are entering the basic variables S1, S2 and S3. Next XB column. XB column we have to enter the values of the basic variables. That is in the initial basic feasible solution we find S1 equal to 50, S2 equal to 100 and S3 equal to 90. So we are entering that values here. Then next that x1. X1 column is the coefficients of the x1 in the constraints. So in the three constraints, the coefficients of x1 are 2, 2, 2. So here we are denoting 2, 2, 2. And then similarly for x2, we have 1, 5, 3. So here we are entering 1, 5, 3. And S1, what is S1? The coefficient 1, other two are 0. So 1, 0, 0. S2, 0, 1, 0. Similarly, S3, 0, 0, 1. So the body of the matrix here, as it is in the given in the what is it in the algorithm, here it is the body of the matrix. This one is the unit matrix and for the basic variables matrix, coefficients of basic variable forms the unit matrix. Okay, then next is a j minus cj. We have to calculate is a j minus cj. So first according to the corresponding x1 column, we are having z1 minus c1. z1 minus c1 is, what is that? Yeah, CB x1, coefficient of x1 minus c1. C1 is here 4. So 0 into 2 plus 0 into 2 plus 0 into 2. That is 0, 0, 0 minus 4. So we are getting the value as minus 4 here. Like that for x2, 0 into 1 plus 0 into 5 plus 0 into 3 gives 0. Cj is 10. 0 minus 10, that gives you minus 10. Then 0 into 1, 0 into 0, 0 into 0, totally 0. 0 minus 0, 0. So like that here also we are getting 0, 0. Then we are having, now we have to examine the sign of Zj minus Cj. Zj minus Cj, two values are negative. So we have to find so we didn't obtain the optimal solution now. So we have to form the next iteration, first iteration we have to go. So here it is most negative we have to choose. So here the most negative is minus 10. So this column is called pivot column. Pivot column. Now we have to find the pivot element. How do you find the pivot element? As given in the simplex algorithm, we have to see the ratio. Ratio is minimum of xbi air. That is this column we have to consider x2 column, and xb is 50. First ratio is 50 by 1. That gives you 50. Second, 100 by 5, 20. 90 by 3, 30. Then among this, we have to find the minimum. So minimum is 20. The corresponding element in the pivot column is 5. So this is the pivot element. So this variable S2 is leaves the basis and x2 enters the basis. Okay, x2 is the entering variable, s2 is the leaving variable. Then next we are finding that leaving variable. Now we are going to construct a new table. For that we are using this formula. First thing is to form the table. First we have to enter the second, that is the pivot row. Pivot row. Before entering the pivot row, we have to divide this row by the pivot element 5 to make it this element as 1. So we get 100 by 5. 100 by 5 is 20. Then 2 by 5 and 5 by 5, 1. 0 by 5, 0. 1 by 5, 1 by 5. 0 by 5, 0. This is the new row in the first iteration table. See here, 20, 2 by 5, 1, 0, 1 by 5, 0. Now we have to find the first row, new first row and a new third row. For that, we have to follow this one, new S1 equation. S1 equation is old S1 equation minus corresponding column coefficient. Corresponding column coefficient is 1 only. So we have to multiply by that 1 into new pivot equation, this equation. So we are getting 20. 2 by 5, 1, 0, 1 by 5, 0. We have to subtract. We are getting the new equation is 30, 8 by 5, 0, 1 minus 1 by 5, 0. So it is the second first row. Then the third row. For getting the third row, here say the old row, existing row, we have to write here 92, 3, 0, 0, 1. Then we have to multiply this new pivot row by 3. Because here it is 3 only in that column. So we have to multiply this by 3. We get 60, 6 by 5, 3 and 0, 3 by 5, 0. Then we are getting that 30, subtracting we are getting 4 by 5, 0, 0 minus 3 by 5, 1. Now what is Zj minus Cj? Zj minus Cj here again after completing that column. Before that here YB is CB. What is CB? The new column YB variable column only we have to enter first basic variables S1, X2, S3. So the values of objective function of S1 is 0, X2 is 10, S3 is 0. Then their corresponding values here we entered all the rows. Now we have to find Zj minus Cj as in the previous table. We get that 0 into 8 by 5 plus 10 into 2 by 5, the plus 0 into 4 by 5. So we are getting that 4. 4 minus 4 is 0. In the same way, we have to find these values also. Now we are seeing that all Zj minus Cj greater than or equal to 0. So by using our simplex algorithm, the current basic feasible solution is optimal solution. So what is the solution? Solution is we have to substitute the values of what is the value of x1. X1 is the non-basic, so it is 0. X1 is 0. X2 is here, it is 20. Value is 20. Then if you substitute these values in the objective function, we get z equal to 200. So it is the optimal solution of this LPP. So in this section, we saw the definition of LPP and how do you convert the given LPP into its standard form. Then the simplex method algorithm, simplex algorithm, and one example under that simplex algorithm. Thank you.